So today we will be going over some combo together, combinatorics, and we will progressively try to build some concepts that ultimately will help us solve some more advanced combo problems, okay? And some of the subjects that we will be covering, I think I will start with some combinatorial identities. Pretty much the ones that you are probably familiar with mostly. Then we will talk about partitions and a little bit of partitions. Then we'll talk a little bit about recursion in general. And finally, the Stirling numbers that I think so of the first and second kind. We'll first study the second kind and then the first kind, which is slightly more involved than the first kind. So these concepts are so much connected that it's better to study them together rather than just to memorize a bunch of formulas. All right, so let's begin. And at the end of the class, I will also share with you guys some resources that I have used while gathering these notes. All right, so let's start with the first problem today. Question number 1. If I were to ask you to give me the sum of these combinations, 4 choose 2 plus 5 choose 2, what would be your answer to this? Yeah, you don't have to raise hand directly. Yeah, give me the answer would be fantastic. Okay, so yeah, I think unanimously most of us have the correct answer of 20. So 2 choose 2 is just 1, plus 3 choose 2 is 3, plus 4 choose 2 is a 6, and finally 5 choose 2 is 10, for a total of 20. But quite a few of you realize that 20 is just a special number. This is just 6 choose 3. And good. So then you start questioning it, right? So you might wonder, why does this thing work? How is these things related to this thing over here? How can I make the calculation basically? Hockey stick, yes, that's the formula. So basically I'm asking to find the logic behind the hockey stick. Usually whenever you have combinatorial identities like hockey stick, there is a logic, like an algebraic way to establish the results. Oh, wow. So you guys are pretty good. All right. We can do induction. We can use algebraic tricks like clever proofs, or we can come up even with a combinatorial argument, which is the best. Okay, you guys already mentioned, quite a few of you are suggesting I should use Pascal's identity, and I think it is reasonable to use that. So just to remind you of Pascal's identity, Pascal, well, you probably already know Pascal's identity, right? Let me not state it. So let's directly, the trick would be the following. Let's call this sum as S. I will just rewrite S as the following. I will just change the very first term. Instead of writing it as 2 choose 2, I will write it as 3 choose 3, which is the same thing. It's still a 1, right? And I'm not going to do anything to the remaining numbers. Why would I do that? So let's apply Pascal identity. Pascal identity says 3 choose 2 plus 3 choose 3 is equal to what? 3 on the Pascal triangle. Yes, that would be 4 choose 3. 4 choose 3 now. And we still have a 4 choose 2. And then it's a 5 choose 2. Well, 4 choose 3 plus 4 choose 2 is equal to what? That's 5 choose 3. That is correct. And we still have the 5 choose 2. Finally, 5 choose 2 plus 5 choose 3 is indeed 6 choose 3. What type of a proof is this? This is one way to prove the result, right? So this is a first proof. This is more algebraic, yes, a clever trick that we did. So you can call it algebraic manipulations if you want. So that's pretty good. But let's see if we can come up with yet a second proof of this result using combinatorial logic. Yes, there are different types of combinatorial logics, committee formations, block walking, and all these other variations. Yes, we can use those. So how can I make such a thing. So which side is easier to interpret? The left-hand side or the right-hand side? Which side is easier? Yeah, the right-hand side is very easy to interpret, right? We have probably 6 objects, and I might as well just, oops, let me just get rid of this. We have 6 objects. Let's call these objects as A, B, C, D, E, F. And all I do is I count the number of ways to form committees of size 3. So let's go ahead and do that, I guess, huh? So let me just go ahead and write out all the committees of size 3, and then let's see if we can somehow split them in this fashion, basically. All right, so here we go. Committees of size 3, ABC. Oops, that's a B, believe it or not. ABD, ABE, ABF, ACD, ACE, ACF, ADE, ADF, AEF, BCD, BCE, BCF, BD. I'm trying to be as organized as possible. Do you guys see that? BDF and BEF. I think I'm done with the ones which starts with a B. And then CDE, CDF, CEF. What's remaining? DEF, yes, thank you. DEF. Are we done? Yeah, it seems. Okay, so how in the world, do we have 20 here? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 20. Yes, we have the 20. So how do you suggest that these 20 somehow can be split as such like this? Fortnite is a, oh, wow, you guys are pretty good. Yes. Why don't we just organize them by the first letter? When I say first letter, do you guys see that in all of these, I organized them in alphabetical order already? So we can just group the ones which starts with an A. These are all the ones. How many of them do we have here? How many of them starts with an A? 10 of them. I wonder why 10 of them starts with an A. Can someone tell me why 10 of them starts with an A? 5 choose 2. Why 5 choose 2? Because we already know that one of them is an A. We need to choose 2 more guys next to it. And because we have only 5 left, once we use the A, there's 5 other letters left. So obviously 5 choose 2. Next, we can go to the other one, right? Wow, so my machine is heating up pretty badly. All right, so then we have the ones that starts with a B, but we can apply the same logic here. So those that starts with a B, how many of them do we have? 4 choose 2 of them, yes. 6 of them, which is just 4 choose 2. And we are not surprised to see 4 choose 2 because they already have all these 3-person committee or 3-letter committees here. They all starts with a B, and we need to choose 2 more letters next to them. Do you guys see that? And we can't choose an A because all the ones which had an A, we already used them. So there are only 4 letters left, namely C, D, E, F, and we need to choose 2 of them. And that's pretty much the idea, right? So next I can choose the ones which starts with a C, which has a C in it, and no A, no B. There is 3 choose 2 of them, 3 of them. And lastly, this one, 2 choose 2. Hey, that's a combinatorial argument to prove that 2 choose 2 plus 3 choose 2 plus 4 choose 2 plus 5 choose 2 is indeed equal to 6 choose 2, 6 choose 3, I should say. So that's pretty good. Yay, we did it. All right, so next. Okay, so I can give you a couple of other examples like this. For instance, some of you guys ask me what is the Pascal identity. Let's quickly double check that. For instance, Pascal identity is, let's write that down. Pascal identity enables us to draw the Pascal triangle, right? So it is n plus 1 choose k is equal to n choose k plus n choose k minus 1. All right, there are 2 ways we can prove this result. How can we prove it? How can we prove this? Yes, we can either come up with, again, a combinatorial argument, Either it can be block walking, or it can be a committee formation, or we can come up with a nice algebraic trick. Yes, that's usually the way we do it. Exactly. So algebra is easy, right? All you do is you just add up these two. We know how to expand these things, right? So n factorial over n minus k factorial and k factorial. You can pretty much do the same thing for the other one. K minus 1 factorial, n minus k plus 1. Oops, messed up again. Okay, plus 1 factorial. Okay, that's pretty messed up. Okay. All right, anyhow, so you guys get the idea. And you can find the common denominator and then clean up the mess, and you should be able to get this result. Alternatively, let's find the combinatorial argument for this. What would be a good combinatorial argument? So how should we handle this thing? Yes, we have n plus 1 persons, and we want to choose k of them. Let's call that extra person, that plus 1 guy, let's call him Joe. Either Joe will be one of these k peoples or not, right? So in a sense, the combinatorial argument again will be a case work. Here is Joe in or out in this case. Who is Joe? Joe is the plus first guy, one of the n plus 1 people. Here Joe is out. Yes, Joe out. Because Joe is definitely not part of the k people, among the remaining n people, we still need to choose k of them. Great. Now, what if Joe is in? The second case would be, this is a case work, right? If Joe is in, then there are n other people left, and among these n other people, we want to choose k minus 1 of them, because in total, we want to find k of them, and that's it. We have, this is a combinatorial proof for this very nice Pascal identity. I think it's very straightforward. Now we can indeed go ahead and one of the benefits of knowing about the Pascal identity is to be able to construct a Pascal triangle. Let me go ahead and construct this triangle. So on top of the triangle, we have 0, choose 0. Then, and by convention, that's just 1. 1, choose 0, 1, choose 1. 2, choose 0, 2, choose 1. 2, choose 2, 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3. I'll go a little bit more. 4, choose 0, 4, choose 1, 4, choose 2, 4, choose 3, 4, choose 4. Why am I doing all the way here? 5, choose 0, 5, choose 1, 5, choose 2. Do you guys see how am I constructing this triangle? All I'm doing is applying this identity here. We know that these two terms, 4, choose 1 plus 4, choose 2, applying in this formula will give me 5, choose 2. And that's how I am able to find the terms underneath each of them. 5, choose 4, and then 5, choose 5. Remember earlier the problem that we solved? It was, what was it? It was 2, choose 2, plus 3, choose 2, plus 4, choose 2, plus 5, choose 2, and the answer is what? The answer is 6, choose 3, right? Which is right underneath that. So, and that explains why we call this the hockey stick identity, right? Because when you think about this shape, it looks like a hockey stick. Yeah, that makes sense. And okay, so we will come back to this triangle in just a few minutes again. This concept is very important to be able to like apply these combinatorial arguments. Here's another question. So for instance, problem 3. What if I ask you guys, let's say n choose 0. For instance, what if I ask you to sum one individual row like this? If I add up all these numbers, what would be the sum equal to? The sum of all these numbers on the third row. Yes, 1 plus 3 plus 3 plus 1, that would be 8. But you guys, some of you suggested 8 is a special number. This is the third row. So we have a conjecture. Our conjecture is what? That this is equal to 2 cubed. If our conjecture is right, that should be also the case for the next row as well, is it? I think it is, right? So that row, what is the sum of this row? Ah, so you guys are amazing. Yes. So the sum of this row is 16, which happens to be 2 to the 4. That brings us to the following claim then. I'll just go ahead and make a claim here. Oops. There you go. All right, so my claim would be the following. M choose 0, N choose 1, plus N choose 2, all the way up to, let's say, N choose N. Then we claim this is 2 to the N. How can I prove this claim? Yeah, okay, so you are suggesting to use binomial theorem. That's one way to handle it, right? This will be an algebraic trick. Yes, IDAN has it. Or we can do a committee forming type of argument. Exactly. So the algebraic trick will look like this. If you check 1 plus 1 raised to the nth power, and if you already remember your binomial expansion, that would be exactly n choose 0 plus n choose 1. That's exactly what, right? So because n choose 0 times 1 to the n choose 1 times 1 to the n minus 1 times, yeah, so it should make sense. That's exactly the sum that we need, but 1 plus 1 is just 2. So that's just 2 to the n. Aha. So that would be an algebraic way to work it out. What would be a combinatorial argument for this? Okay, so in the meantime, because my computer is overheated, I'll just open it on another page, the chat box, because let me see if I will be able to log in. I hope I can. If I can't log into my own session, okay, while you guys are thinking, 997-634. Probably the system won't let me, right? 693. Let me see if I can log in from another computer. Oh, wow, I need to first register. Okay, so forget about registering. All right, so how do we do this? Using a combinatorial argument. Okay, so what we are doing on the left-hand side, okay, let's start with the left-hand side. On the left-hand side, so what we are doing here, n choose 0, n choose 1, n choose 2, n choose n. So n choose 0 will tell you the number of ways to come up with size 0 committees. N choose 1, how many size 1 committees, how many size 2 committees, and so on, how many size n committees. The total number of committees of all sizes on the left-hand side, total number of committees of or subsets of all sizes, that's just, there's another way to count it, and we can do a constructive counting argument, right? That's exactly how I can interpret the right-hand side, actually. So what I can do is, the first person is either in the committee or not. The second person is either in or not. The third person in or not. For each person, there's a binary choice. 2 ways, so 2 to the n as a result. We apply the multiplication rule, right? And that's it. That would be a direct combinatorial proof of this really nice thing. Obviously, the Pascal triangle has so many different really cool stuff related to it. There's not much time. So for instance, do you guys know how to relate the Pascal triangle, so this triangle, to Fibonacci numbers? So what was the rule? I forgot to be honest. Wait a second. So how are we doing that? Was it this kind of slant line? Okay, yeah. I think like this, right? So, oops, let me use a different color. Okay, so yeah, you are right. So this would be 1. Then the total here is 1. Then the total here is 2. Then the sum here is 1 plus 2, that's a 3. The sum here is 1 plus 3 plus 1, that's a 5. Do you guys see that? So these weird diagonals, their sum would be the Fibonacci numbers, F0, F1, F2, and so on. So you guys can double check it later on as well. Awesome. So now that we did that, there's so many combinatorial identities that there are even books about these combinatorial identities. Usually it's a very good practice in general to study those combinatorial identities and then to try to interpret them, solve them both algebraically, and then interpret them, just as a maybe homework type of question. So I don't know if you've heard of the Vandermonde identity. Yes, Vandermonde identity. Yes, that's one of my favorite as well. So if you have a group of n girls and m boys, the number of ways you can form a K-member committee from among these N boys and M girls would be N plus M choose K. Well, how can I, so I won't even bother giving you guys the identity itself. So you should be able to, by just that hint that I provided you, N boys, N boys, M girls, and we want to choose K of them. So how can we do that? Either we can do M plus M choose K without referring to their genders, or indeed what we can do is we can refer to their genders, and what we can do is either I'm choosing among the girls, no girls in the committee, after which obviously I need to choose K boys, or if I have one girl in the committee, then I can only choose K minus 1 boys, and so on, right? Do you guys agree? Or all the members are girls and no boys. So these two must be equal to each other. So it would be a super, oh wow, yeah, just like George also mentioned here, it would be a super cool exercise to try to solve this algebraically as well. Combinatorially done, proof, combinatorial interpretation. What did I do here? Interpretation and done. Check. All right, but algebraically how to do it, it might require a little bit more skills, obviously. Okay, so that's pretty good stuff. Now let's go into the second part of this kind of quick review, if you will. I want to talk about partitions next. Partitions. And the question then is, if the main question that I want to answer is, how many ways can you, okay, let me write that down. The main question I'm thinking about is, if you have n indistinguishable objects, the question is, what is the number of ways you can group them? What is the number of ways to group these objects, to group them? And when I ask you this question, you need to ask me back another question. What would be the question? Stars and bars, bagels, donuts. Anonymous. Okay, you guys are pretty good. All right, so we have these indistinguishable objects. What's the number of ways to group them? Okay, so let me ask the following question now. Okay, so let's put it as a question. So problem, is it 4 or 5? Let me check. I think that's 3. Oh, well, the homework was 4. Let's claim that homework was 4. Let's do problem 5, for instance. My question is very easy. In how many ways can we partition? In how many ways can we? Obviously, this is not stars and bars. Why? Because the groups are indistinguishable in a sense. Huh? So, well, okay. So we'll see that. In how many ways can we say partition 5? Partition 5. Okay, that's my question. In how many? This is not a homework. In how many ways can we partition? Yes, we will come to Ramanujan's soon. And a little bit of generating functions, yes, but not yet. So in how many ways can we partition 5? Well, you can ask me a further question. The question would be what? When I ask you how many ways can I partition 5, can I write it as a sum of smaller pieces? One thing that we need to agree on is, does order matter? Does order matter? Okay, so question, does order matter? Okay, if the answer to this question is, let's say for a minute that the answer is yes, order matters. So here we go, 5. Or if you want, I can put equal signs between them. It's up to you. So we can have 4 plus 1, or we can write it as 1 plus 4. Do you guys agree? Just 7? I thought there was more. Oh. All right, so what else can I do? I can do, because order matters, right? So we are giving the answer to the question, if order matters, then yes, 3 plus 2 plus 2 plus 3. What else can I do? Yes, thank you. 3 plus 1 plus 1, which is the same thing as 1 plus 3 plus 1. Because order matters, I need to write all the arrangements. Yes. Yeah, you are not allowed to use zeros. Yes. And then we have two more things to worry about. So 2 plus 2 plus 1, 2 plus 1 plus 2, which is 1 plus 2 plus 2, or like you guys said, 2 plus 1 plus 1 plus 1, 1 plus 2 plus 1 plus 1, 1 plus 1 plus 2 plus 1, and one more, 1 plus 1 plus 1 plus 2. All right, and lastly, I think there's one more, right? And then a bunch of ones. 1 plus 1 plus 1. Did I skip any? Let's count how many I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 16 of them. Okay, let's make a conjecture. Okay, I'm pretty good in making conjectures. No one is annotating. Okay, my conjecture is because the answer is 16, I claim I can relate 16 to 5 like this. It is 3 times 5 plus 1. Okay, so as a result, my conjecture, I told you, I'm pretty good in conjecturing. My conjecture is that whenever you have a number n, the number of ways to, when order matters, let's say call it Qn. Qn is number of ways to partition a number when order matters, is 3 times n plus 1. What do you think about my conjecture? I'm naturally great, right? Yeah, so some people are not happy. So what would be an easy way to convince me that this is a very bad conjecture? How can you quickly convince me this is not good? Yes, test with another number, right? Exactly. So for instance, let's test with, say, 3. Q of 3 apparently is supposed to be this, 10. And sure enough, if I were to do the same action for 3, 3 can be written as 3, or it can be written as 2 plus 1, or it can be written as 1 plus 2, or it can be written as 1 plus 1 plus 1 plus 1. That's it. 4 ways, it seems, is the correct answer. So Q sub 3 is not equal to 10. Indeed, Q sub 3, we need to find another formula which will, oh, wait, did I mess up? Oh, sorry, there's an extra one. There you go. Yeah, so, okay, what do you suggest? What would be a better formula? So there's yet another conjecture. Okay, so this conjecture was pretty bad. So this is, forget about this. So this conjecture is really bad. Instead, there's yet another, a better conjecture, hopefully. Okay, actually, let me write the conjecture right next to it. So you guys are suggesting that Q of n, where Q represents number of partitions where order matters, is equal to 2 to the n minus 1. And sure enough, again, the same story. We should be able to prove it using algebraic tricks like induction or some other stuff. But, or we can come up with a combinatorial argument. Okay, I'm all ears. Give me your combinatorial stuff. Why would the number of ways to partition a number when order matters be equal to 2 to the n minus 1? There you go. Okay, a couple of you, Aaron already gave the correct answer. And okay, so basically what we can do is we can start with 5, for instance, and we can represent them as 5 dots, let's say. These 5 dots, so suppose that I want to partition 5 where order matters. So it has between them 4 gaps. Do you guys see that? And I decide whether I want to put a bar between those gaps. I have 2 choices for each one of them, right? So suppose that no bar here. Here I want to put a bar. Here I don't want to put. And here I don't want to put. So as a result, this is called a bijection. I think I kind of established a bijection. So here this would be associated with 2 plus 3. Do you guys agree? Which is obviously here. So in total, there are 16 ways to decide whether we want to put a bar between the gaps or not, 2 to the power n minus 1, and we would be done. In this case, 2 to the power 4. That's pretty good deal. What? Telephone? Hey, what's that hat? Okay, back to story. All right, so when order does matter, I think that's kind of the idea. Do you guys, let me see. Do you guys want to solve a slightly more where order matters? Okay, while we are doing it, okay, it will be a little bit of diversion, but okay, let me ask you yet another question. So pretend order matters. Order matters. How many ways can you partition 5 where you are not allowed to use ones? Okay, so order matters partition without using ones. How many ways for instance, in the case of 5, how many are there? We can write it as 5, or yes, 3, 2, 2, 3, or that's it. 3 plus 2, or 2 plus 3. So the answer would be, let's call this q sub 2, because, or let's call it q sub, okay, let's call it q prime. Q prime means you are not allowed to use 1, okay? So q prime of 5 apparently is equal to 3. Can you tell me what q prime of 6 is? What is q prime of 6? You guys are really good. 4 plus 2, or 2 plus 4, or what did you say? 3 plus 3, 4? Is it 4? Wait, why 5? 7? Oh, 2 plus 2 plus 2. Thank you, Catherine. Yes, there's also 2 plus 2 plus 2 plus 2. That's it, right? So that's 5. Okay, what would be your conjecture? So let's call this, yeah, so what would be a formula for q sub prime of n? Anyone can see a formula? Aha! No way! What does Fibonacci have to do with that? It's like sometimes there's a problem in calculus or someplace, and then suddenly there's pi shows up, right? And usually pi is associated with the circle, so you start wondering, where did pi come from in this whole thing? What does this thing have to do with Fibonacci numbers, right? Okay, so you guys are claiming, this is a bold claim, you know, people can make fun of you, you know. Okay, like this, huh? Okay, so what are the initial conditions? Q prime of n is equal to, oh sorry, Q prime of 1. How many ways can you partition 1 under these conditions? 0 ways, that's correct. Does everyone agree? Because we are not allowed to use 1. How many ways can we partition Q prime of 2? How many ways can we partition 2? 1 way, that's correct. And that's pretty much it. So, and you guys can check. And yes, if you test the first few occasions, you will see that it will work. Now we are in the hard part. Why? So this should follow. So whenever you have a recursion, this is a recursive form, just like in the previous exercises. So then we need to come up with a combinatorial argument, recursive argument. These are all recursions. So what are the two cases? So apparently there are two cases. We have this case, and then we have the pink case. Which case should I start it with first? Oh, shoot. Okay, my screen is pretty messed up. All right, which case should I start with? The pink case or the red case? What is the casework? Again, remember, order matters. Where does the pink come from? Well, okay, so let me tell you where it comes from. So if you have, yes, oh, good, yes. So this is a casework. If the first term is a 2, just check the first term. Okay, so suppose that you have n terms, and you already have a partition with n terms here. So all you do is, if the first term of the partition is a 2, just remove it. So you are left with a legitimate partition with n of a number n minus 2. Do you guys agree? Or if the first number is not a 2, remember order matters, right? If the first number is not a 2, now this is the red case. If the first number is not a 2, just subtract 1. Yes, That's it. Just like dotted calculator said, just subtract 1 and you are done pretty much. So that will give you the recursion, and this is a good recursion actually. All right, I think that's enough for the partitions where order matters. Oh, actually, we are really behind the schedule. So let me go ahead and, yeah, we can spend a lot of time. I enjoy these subjects, but let's directly go to where order matters. So if the answer, remembered my earlier question, does order matter? If the answer is yes, we looked at the situation. If the answer is no, if answer is no, meaning order does not matter, order does not matter, then, then under these circumstances, let's call the solution as P of, if order matters, we called it Q of. So for instance, P of 5, if order does not matter, how many ways can I partition 5? Well, I can write 5 as 5, or I can write it as 4 plus 1. By convention, I can write the larger numbers in front and then the smaller numbers after that, right? Okay, so what else next? Come on. Yes, then I can write 3 plus 2. Then I can have 3 plus 1 plus 1. What else? Oh, yes, 2 plus 2 plus 1. Thank you. 2 plus 2 plus 1. And what else? 1 plus 1 plus 1 plus 1. 1 plus 1 plus 1 plus 1. Did I miss any? Yeah, oh, yeah. Twin brain, thank you. I missed also 2 plus 1 plus 1 plus 1. Yes, okay. 1, 2, 3, 4, 5, 6, 7. It seems P5 is just a 7. Well, what you can do is, let me go ahead and write out, before the class, I tried a few of them. Let me write out the first few of them. So P1 is a 1. One way you can really do it. P2, if you try P2, that would be 2 ways. Either you can write it as a 2 or 1 plus 1. P3 can be written in 3 ways. P4 can be written in 5 ways. P5, we just did it, can be written in 7 ways. P6 can be written in, I think, 11 ways. P7 in 15 ways. So 7 can be partitioned in 15 ways. 8 can be partitioned in 22 ways. 9 can be partitioned in 30 ways. The reason we are doing it to see if we can find a pattern, right? Which is very difficult in this particular case. 11 can be partitioned in 56 ways, believe it, and so on. Okay, I won't go further. Some of you guys already mentioned, one of the books that I benefited while preparing this kind of workshop is Conway. He has a very good book, the Book of Numbers. That's a really, really nice book, and it kind of gives you some brief information about all these different type of good numbers. I mean, like number series or patterns. Yes, so yeah, not the Game of Life. Conway, the Book of Numbers. Very neat book. All right, so it turns out there is no no nice one, it seems, except you can come up with some algebraic tricks. Let me show you 2 algebraic tricks. Well, obviously, some of you already mentioned the recursion. Yes, there is a recursion, but it's a rather complicated recursion. Let me show you the recursion first, and then I can show you a better way, an algebraic way to manipulate these numbers if you need them. It's kind of a little bit more advanced, but Euler had this following idea. This one is available on Conway's book. So Euler did the following recursion, believe it or not. Pn minus, so Pn minus 1 minus Pn minus 2 plus Pn minus, I believe, 5 plus Pn minus 7, and so on. So 2 pluses, 2 minuses, so with the exception of the first one. So if you continue this pattern, and I think this ends up being equal to what we call as 0 to the power n. The reason we call it 0 to the power n is 0 to the power n is equal to 0 if n is greater than 0, and it's equal to 1 if n is equal to 1. Okay, so meaning P of 0 is actually 0. Sorry, P of 0 is actually 1. Sorry, my bad. All right, so where does these numbers come from? 1, 2, 5, 7, and more like 12, 15. They are pentagonal numbers. All right, let me just remind you of the pentagonal numbers. So what you have is, well, you have triangular numbers. The triangular numbers, an easy way to write out the pentagonal numbers is to start with triangular numbers, which you all know, 0, then add 1, then add 1 and 2, so 3, add 1, 2, 3, that's a 6, 1, 2, 3, 4, that's a 10, add 5 to this, add 6 to this, add 7, add 8, and so on, right? So 36, add 9, 45, what's next? 55, 55, at 10, at 11, 66, and so on. So an easy, sorry for that. An easy way to find the pentagonal numbers is just to check the ones which are divisible by 3. Do you guys agree? And just divide them. All right, so let's do it. So the ones that are divisible by 3, you just divide by 3, and that will give you the pentagonal numbers. So 0 is divisible by 3, skip this one. 3 is divisible by 3, 2, skip this. 5, 7, skip this, not divisible by 3, 12, 15, and so on. So these would be your, yeah, okay, good. So yeah, you guys could try to remain, what do you call it? Civilized. I know there's a lot of excitement in the chat box, which is good. I mean, we are excited about math, right? So, yeah, so the only thing is, how about the signs? Like we said, the signs will go 2 minus, 2 plus, 2 minus. For instance, if you apply the recursion for P12, remember earlier I stopped at P11, we found that as 56. So P12 will be just, oh, sorry, P12 minus 1, which is P11, P12 minus 2, which is P10, add now P7 and P5, add P7, add P5, and the next one would be these two, P12. Okay, so just subtract P0 and that's it. So this thing is supposed to come out as 0 to the power 12, which is just 0. If you just plug in all the values, P12 minus, so P11 is 56, just like the list that we just did here. P10 is 42. P7 was, oops, I can't see from the chat box here. Okay, yeah, there you go. So let me move away the chat box. Yeah, P7 is 15, that's right. P5 was 7, minus P0 is a 1, and that's it. This is supposed to be equal to 0. So if you solve it for 12, that should come out as 77. Yes. Okay, so this one is almost magic, right? So I mean, who would have thought about this recursion? See if you can find an algebraic argument to explain why this thing is true, right? But I want to show you guys an alternative, which is an algebraic way to handle it, and it is also somewhat useful when we go ahead to check the Stirling numbers, and it's the following. Algebraically, this is the same as this one, believe it or not. 1 over 1 minus x, 1 minus x squared, 1 minus x cubed, and so on, an infinite product on the denominator, and this thing is apparently equal to 1 plus p of 1x plus p of 2x squared, where the p of n is the number of what's it called, partitions, where order does not matter, p of 3x cubed, and so on. How can I prove this? The proof is relatively easy for this one, even though it looks extremely intimidating. Let me put some space on top. It turns out that, yeah, the proof is really really nice. Yes, but first let's start with some trick. What trick? On the left-hand side, I need to do something. What is that something? No, this is a 1.5 hour class, so we will end at 3 p.m. Yes, infinite geometric series. Yes, sir. So let's do it. So first, I can basically split all of these as 1 over, right? So and then so I can write them as 1 over 1 minus x, 1 over 1 minus x squared, and so on. An infinite amount of them. Let's double check the left-hand side and let's try to explain why these coefficients are what they are. All right, so let's do it. 1 over 1 minus x, an infinite geometric sum, that's just easy. 1 plus x squared plus dot dot dot. How about 1 over 1 minus x squared? pretty much the same thing. You just plug in x squared into it. 1 plus x squared, right? Plus x squared squared. All I did was into this formula, I plugged in an x. That's it. X squared, I mean. Then I do the same thing here. 1 plus x cubed plus x cubed squared, and so on, and so on. So that's the left-hand side. Now, how can we make it match the coefficients of the left-hand side and the right-hand side match? Oh, Central Time, 3 p.m. Yes, we will end in 40 minutes. All right, so this is the left-hand side. For instance, let's check the coefficient of one of them. For instance, how about, exactly, how about I want to check the coefficient of, say, x to the 6 on the right-hand side. The coefficient of x to the 6 is p of 6 on the right-hand side. And this is supposed to be equal to the coefficient of x to the 6 on the left-hand side. How can I find the coefficient of x to the 6 here? From the first term, I can either select casework. Yes, I can check x to the 6th power. That's one way to do it. There will be an x to the 6, one of them from the first one. Do you guys see that? So x to the 6, I can factor out that thing. So all I will do is, this is the coefficient of x to the 6 on the right-hand side, and I'll check the coefficient of x to the 6 on the on the left-hand side. So here, x to the 6 has a 1 in front of it. That's one way I can get it. Plus, or what I can do is, for instance, I can take, let's say, I don't know, I'm just making it up. I can take one of this, I can take one of this, and I can take one of this. Do you guys see that? That will be another one from there. They will multiply out to x to the 6. Or, indeed, I can maybe even take out like this. I can take out, let's say, 2 of x squares, and maybe what? X to the 4. So then it means I can take this one. So this one can be reinterpreted like this. X, 2 of them here. So for instance, if I were to take this one and this one, what would be, okay, so what does it, will it be associated with in terms of 6? So what does it represent? If I were to take this guy and this one. Yes, so x squared represents a 2 on the exponent, and we are picking 2 of them, so 2 plus 2. And the x to the 1 here, we pick 2 of the x to the 1, so 1 plus 1. Aha! This is one of them where order does not matter, right? Do you guys agree? So whenever you pick here, so we interpret x to the 6 here, we interpret it as x, 6 of them. Right? So for instance, in the first case, if I just pick this one and 1 from all the others, meaning 0 of the others, because it means x squared to the power 0 here. And this means x cubed to the power 0. You guys see that? So as a result, if I were to pick this one, that's equivalent to picking 1 plus 1 plus 1 plus 1 plus 1 plus 1. Ah, that's good. How many comments? I don't know. A lot. You guys are very active. Okay. So it turns out there's no good closed form formula. Well, there is a closed form formula, believe it or not. But you guys already mentioned that there is some approximations. And a well-known approximation by Ramanujan is the following. Oh gosh, pencil. All right. So it's an asymptotic. So it works better. Yeah, sorry for that. Yeah, asymptotically it works. It is asymptotically equal to 1 over, oh, decline, 1 over 4n root 3 and exponential pi square root of 2n over 3. That's it. So this is a pi. Again, a circle appeared somewhere. So this works really nice as n grows larger and larger. When we say it works nice, what we really mean is as a proportion, it approaches like the error term as a fraction approaches 0. Okay. All right. So if you want to learn more about this subject, where can you learn more about this? On YouTube, there's a very good thing on YouTube about this. Wikipedia, AOPS, Khan Academy. Not Khan Academy. It is Number file. Number file has a special video about this, so you can search it after the class if you want. They talk about these approximations and things like that. They have a whole video, like episode, where they talk about partitions. Actually, there's more than one actually, so it's pretty good. Not on my YouTube channel, no. I don't mention this on my YouTube. I think. Well, there's a couple of Olympiad questions, IMO questions, which required partitions that I used it over there, but other than that, I didn't. I didn't check 3 brown, 1 blue, maybe over there, or 3 blue, 1 brown, sorry. Yeah, there might be some discussion about partitions as well. Okay, I don't want to go further about partitions. Obviously, this is a very deep topic that we can keep discussing forever, but yeah, so because we are running out of time, so now the remaining 30 minutes, let's go dive into the following subject of Stirling numbers. So that's the last part of today's class, or whatever you call it. So Stirling numbers, social interaction, let's call it, because the chat box is more interesting than me lecturing, I guess. People are, oh, wow. Okay, so very nice. All right, so Stirling numbers. There are 2 kinds. We will start with the second kind. So basically, the idea is very simple. If you have n distinguishable objects, distinguishable, that's important. Okay, so this is definitely wrong, but okay, so fine. Objects and k indistinguishable boxes, wishable, how do you spell this word? Okay, boxes. How many ways can you put those undistinguishable objects into these k boxes such that what? How many ways to place those objects such that there has to be a restriction? What is the restriction? There's a constraint. Yes, such that at least one object in each one, at least one object in each. So that's the first question that we want to address. Just for an example, suppose that you have 4 objects. How many ways can you place these 4 objects into one box? 4 objects into one box. One way, that makes sense. Remember, the objects are distinguishable. So for instance, you can think of them as A, B, C, D. Those are our 4 objects, or maybe I can write it like this, A, B, C. You're trying to put these objects into the boxes. Okay, good. How about 4 choose 2? When I say choose, I really mean this new notation. This is a different kind of choosing, right? So how many ways can I put those 4 objects into 2 boxes now? This is a little bit, we need to be careful. How many ways can we put these? Well, okay, so one of the answers is, well, because we have 2 objects, so 4 objects, each one has 2 choices. The answer should be 2 to the 4, which is 16. Why? Because each one has 2 choices. So suppose that these are our 2 boxes. So A have 2 choices, B have 2 choices, C has 2 choices, and so on. What's wrong with that? Yes, we need to apply principle of inclusion and exclusion, and because there's the possibility that one of the boxes will remain empty, right? So as a result, that's not a good way to do. Instead, what we can do is we first check the cases. There are 2 cases when you place these 4 objects into 2 boxes. What are those 2 cases? Yes, 1, 3, or 2, 2. That's pretty much the number of ways to partition 4, right? The number of ways to okay, so to partition 4, well, -1 because okay, into 2 boxes, into 2 pieces. Okay, so it's slightly different than the number of ways to partition 4. All right, but the number of ways to split 4 into 2 pieces is either 3, 1 or 2, 2. So let's do the easy case. What if 3 objects here, 1, 2, 3, and 1 object here? How many ways can we do that? 3 objects, yes, 4 ways. Why? Because we need to decide which object will be lonely on its own box, and the other 3 will go to the other box. That's easy. How about 2, 2? How many ways can we put these objects into these 2 boxes? Yeah, 4 choose 2 ways. Oh, some people are not happy with 4 choose 2. They suggest it should be 4 choose 2 divided by 2. Why would they say divide by 2? Symmetry, yes. The boxes are indistinguishable. That's why we need to divide by 2. And this is indeed a 7. As you can see, this is a non-trivial problem that requires some care. How about 4 objects into 3 boxes? Luckily, how many cases are there for this one? What is the only case you need to check? Oh yeah, ultimately this is connected to Burnside lemma. And Burnside lemma is ultimately connected to quantum mechanics. So if you want to learn advanced physics, yeah, you can use abstract algebra a lot to do to check. Okay, yes, 4 objects into 3 boxes. There are 3 boxes. There's only one case, 2, 1, 1, right? So 2 into 1 box, which we can choose 2 ways, and that's it. And the other 2 objects goes into the other 2 boxes. That's easy. 6. And finally, if you have 4 objects and you want to put them into 4 boxes, how many ways can you put those 4 distinguishable objects into 4 indistinguishable boxes? 1 way. You put 1 into each box and the boxes are indistinguishable. It turns out, so that's it. So you just found the Stirling numbers for 4, right? In fact, there's even a formula. There's also something called Bell numbers. Bell 4 would be just the sum of those things. 4 choose 1 plus 4 choose 2 plus 4 choose 3. When I say choose, you know what I mean. In the notion of 4 choose 4. And if you were to add these numbers, what does it come out as? So 1 plus, we just found this one is a 7 plus 6 plus 1, and that is a 13, 15. That's interesting. All right, so we can discuss another time about the Bell numbers. There we go. All right, so now next what we can do is, just like in the case of, Pascal identity, let's try to find a closed form formula for, what's it called? For Stirling numbers of the second kind. And then maybe from there, we should be able to find out a very nice relationship connection between Stirling numbers and Pascal triangle and Pascal numbers. Remember Pascal identity? Pascal identity, that was, we just looked at it a minute ago, right? We even proved it actually. N plus 1 choose k is equal to n choose k, meaning Joe is out or Joe is in. Joe is out, Joe is in, that's it. Wait, that doesn't look right. Sorry, Joe is in. Yeah, there we go. All right, Joe out, Joe in. So now let's see if we can find a Stirling identity, if you will, of the second identity, second kind identity. So can I relate n plus 1 distinguishable objects, putting it into k boxes, somehow in terms of a smaller problem? Aha, you guys are good. Yes, it is possible. All right, so you guys can hear me, I hope. Yummy. All right, so don't remind me of food. Why don't we just write it like this? Why don't we make it look like Pascal identity? So do you think that would work? So how should what should be the logic? Oh, after the class, you can watch this recording. We are recording these sessions, right? So these recordings are available on Momentum page, which we also have a YouTube channel. You can go to the YouTube channel as well. All right, so remember this one, we were able to prove it using the fact that Joe is out. We don't select Joe for this, and then we can select Joe here. How about now? How can we interpret this? So because we don't have Joe here, these are objects. So we have n plus 1 distinguishable objects. Again, let's focus on one of the objects. So what would that mean for that object? And what would that mean? Yes. Okay, so yeah, so you guys are already interpreting it very well. So either our object would be lonely in its own box. That's the one. Suppose that your object is Woody. No, yeah, Woody. You remember Woody from Toy Story 4, right? Toy Story 4. So Woody lonely on its own box. And because Woody is lonely on its own box, this means all the other objects has to be packed. There are n other objects remaining, and they will be packed into the remaining k-1 boxes. That's it. What would be the other case then? Yeah, so Woody, not lonely, not lonely. When we say lonely, I mean in its own, it's not lonely in the box, right? So there are already n objects in those k boxes. So therefore, when I choose where to place Woody, I have n choices, but now guess what? Because I'm first putting the other objects into the boxes now are distinguishable. Do you guys agree? So as a result, I need to multiply this by k. Does that make sense? So that is the recursion. Okay, so this case was easy. First, put Woody into one of the boxes, and because Woody will be lonely in that box, there is n other objects left, but only k-1 other boxes. So as a result, and choose k-1. If Woody is lonely, put Woody first. If Woody is not lonely, then first put the other objects into the k boxes. Now Woody is just, it doesn't matter, right? Woody doesn't create a constraint because all the boxes are already full. Remember, that was very important. For the Stirling numbers of the second kind, all the boxes should have at least one object, and we already satisfied that constraint over here. So therefore, there are k boxes, but now the boxes are distinguishable. Why? Because there are already objects in those boxes. So now you decide among those k objects, which are not distinguishable because they have different objects in them, there are k different ways you can choose where to place Woody. So first place Woody, then choose the others. There's only one way to place Woody. Why? Because all the boxes are indistinguishable. Then there's this many ways to put the other objects, and so on. So therefore, I have to multiply it by k. Does everyone agree on what I did so far? So yeah, this is, yeah, so this is important. Now next, let's have a look a little bit deeper. Okay, I'll do two things now. So now that we know this recursion, we can build ourselves a new triangle. This is a Stirling second kind triangle. Let's do it. Stirling second kind triangle, and then from there I will try to find a closed form formula. All right, so Stirling second kind. So we start with, on top we will have we can start with one choose one, and then so if you have one object, one box, versus two objects, one box, two objects, two boxes, three objects, one box, three objects, two boxes, three objects, three boxes, and so on. Let's do one more. Four objects, one boxes, four objects, two boxes, four objects, three boxes, and four objects, four boxes. And it keeps going on and on, just like in the Pascal triangle. We already did the fourth row, right? 1, 7, 6, 1. It's very easy to come up with the row above that. 1, 3, 1, and the one above that. If you have two objects and one box, there's only one way to pack them. Two objects, two boxes, one way to pack them. One object, one box, one way to pack them. I wonder, for instance, what is, so here we have 5 objects, one box, 5 objects, two boxes, 5 objects, 3 boxes, right? 5 objects, 4 boxes. Let's try to calculate, for instance, 5 objects. Let's calculate the whole row here. Let's start with 5 objects, 1 box. How many ways? 1 way. There's nothing much to do with that one. 5 objects, 5 boxes, also 1 way. All right, let's do 5 objects, 2 boxes. 2 boxes. We can just use the recursion, right? Just use the recursion. We just found it. So all we do is just look at the 2 numbers above it, namely 1 and 7. It says multiply the one on the right by its position. This is on the second position, and multiply, don't do anything here. So basically it is 1 plus 2 times 7. That's a 15. Do you guys see that? 1 plus 2 times 7. All right, so this is a horrible marker. Okay, this one, it would be 7 plus 3 times 6. Do you guys see that? And then finally, this one would be, we will use 6 and 1 on top of it. So this one will be 6 plus 4 times 1. Do you guys see why I multiply by 4? Because of this, right? Whatever its position, you multiply with it and then add it to it. So exactly. So as a result, this one comes out as 15. This one is 25. Yes, 25. What is that one? 10 and 1. So therefore, we found our numbers, right? Wait, are they triangular numbers? 1, 15, 25, 10, and back to 1. And that's it. So this way you can expand out and find the whole thing. So that's a pretty good deal. Yeah, I don't think it's triangular numbers or... Nice. Okay, so are you guys ready for a couple step further than that? Okay, so yeah, we will explore a little bit more at this step, and then ultimately my goal is to come up with a closed form formula. All right, so that would be super cool if we can find a close. I mean, not that I don't enjoy this. I mean, this is obviously super nice recursion, which is good enough to me, but we can do even more than that. And you guys already suggested, some of you already suggested what we can. Oh, I see now the triangular numbers. Oh, I thought the second like diagonal, this diagonal brings the, yes, wow, that's pretty cool. All right, obviously maybe for a science fair project, you can write a paper about, for instance, everybody has already investigated the Pascal triangle a lot. Maybe you can investigate this Stirling triangle, and then of the second kind or of the first kind, there's another triangle, and you can try to explore as many properties as of it as you can, right? So yeah, that's another thing. Okay, so if you guys are ready, let's do a couple of things. So for instance, if I were to ask you, what is this number, and choose 1. So we will check properties. Properties. All right, what's and choose 1? N objects, 1 box, 1 way. That's good. Regardless of whatever n is, that's always 1. And choose n. N objects, n boxes. That's 1 as well. All right, hard question now. And choose 2. N objects, 2 boxes. Okay, let me give you a few minutes to think about this one. You have 2 boxes. Holy, that's good. Wow, you guys are amazing. Because we have n objects and we have 2 boxes, what we do is for every object, have 2 choices. They either go into 1 box or the other box. So 2 to the power n, is that what? No. Oh, okay. So what do you say we should do? Okay, let me go back. So are you saying this is the recursion? No. Okay, okay. So we need to think. Okay, let me think as well. I think it is. Why not? So the reason I am subtracting 1 is because there's the possibility 2. I should subtract 2. That's right. That's right. Okay. So it's 2 to the n minus 2. How about that? Okay. People are not happy again. Okay. So let me tell my logic. Okay. So I have 2 indistinguishable boxes and n objects. So n objects and 2 indistinguishable boxes. Each object have 2 choices, right? So, so each object have 2 choices. So we have 2 to the n. But then the reason I subtracted 2 is because I want to rule out what? Why did I subtract 2 first of all? Why did I subtract 2? Yes, there's the possibility that just by pure chance, we are going to put all the objects into 1 box, which is not allowed, or all the objects into the other box, which is not allowed. So I need to subtract 2. But then you guys already suggested these boxes are indistinguishable. So in the end, name doesn't matter. So when I say 2 boxes, 2 choices, like it's as if I did choice A, choice B. That's no such thing. These boxes are indistinguishable. So I need to divide by 2 in the end. Oh, so that's 2 to the n. Okay, sorry. Let me write it again. 2 to the n minus 1 minus 1. Whew, okay, so that was tough. Okay, let's do it for 3. Okay. Why do we do that, Dr. Nal? because we will do the general formula for K. But before we do that, we need to make sure we grow our muscles. All right, and choose 3. Same logic, right? What? I don't understand what the chat box is going on anymore. At the beginning, I was understanding the discussions, but now I'm totally lost. All right, so how about 3? Yes. Okay, let's do it. Let's do it. Let's do it. So 3 boxes, A, B, C. For the time being, I will keep them distinguishable, and in the end, I will just make them indistinguishable by dividing it by what? By dividing it by 3. Is that so? Aha. By dividing it by 3 factorial, right? Because there is 3 factorial permutations between them, dividing it by 6, that's correct. All right, let's do it. Either all the boxes we have n objects, 3 choices for each one of them, 3 to the n. That's our initial count. But this is strategic overcounting, right? So I need to make a, what? Downward adjustment, y6, because we have, if they are distinguishable, like they are supposed to be indistinguishable, these 3 buckets, those 3 boxes. So there is 6 ways to arrange them. So whatever is the outcome in the end, there are 6 ways to permute those outcomes. All right, so you guys can also respond to each other as well on the chat box. All right, so what if one of them is empty? Say A can be empty. So all the objects can go into B or C. That would happen in 2 to the n ways, n objects, 2 choices for each one. However, it might not be A empty. Maybe it's B or C empty. So I need to multiply by 3. Or if you want, we need to multiply by 3, choose 1. How about that? That's even more technical. Okay, let's not confuse you for the time being. Okay, 3 times 2 to the n. Finally, what? I need to make an upward adjustment. This is exactly the definition of what? Principle of inclusion exclusion. Yes, what if 2 of them are empty? Meaning all the n objects go to the C. This happens in 1 to the n ways. But because we can choose which ones will be empty in 3 choose 2 ways, again, I need to multiply it by 3. Did I mess up? Okay, let me know if I mess up. I do a lot of silly mistakes. That's it. That would be the formula. Okay, now, people, what would be the general formula? Wait, is this formula correct? I think it is. So the 1 to the n is just 1, so I don't have to worry about this one. All right, so what would be the general closed form formula? Not only we have a recursive form for the general, second kind, but we even have a closed form. So what would look, yes, it would start as 1 over k factorial, obviously, right? Then we would have a summation sign. Now tell me what's inside the summation sign, term by term. Like that. There will be some of them will be pluses, some of them will be minuses. So definitely there will be a term like -1 to the power something. Okay, so let's do the summation from j equals 1 to k. And yeah, so for the time being, I don't remember. I think it is k minus j. There are multiple ways you can do the index. Then we will have, because do you remember this was 3 choose 1 way to have 1 box empty, or 3 choose 2 ways. So, okay, so there you go. You guys already, some of you already suggesting the answer. Yes, that would be the answer. J to the power n. The logic is exactly what we did here. The principle of inclusion and exclusion. Make sure you understand this thing, all right? Awesome. So let me just get rid of these because, yeah, they are confusing. All right. So initially you are treating them like distinguishable. That's why we need to make this adjustment, 1 over k factorial. And then we sum up all these things, minus plus things. We just sum them up, just we did earlier. And yeah, you can easily convince yourself that this works. All right. Are you guys ready for a little bit more challenging stuff? Okay, let's go a little bit, one step further probably. So I gave you the closed form formula. Okay, before I go one step further, can I just quickly show you the first kind as well, so that we are all covering all of our bases, right? So, and then if you guys want, this is obviously a very deep subject. Oh gosh, Stirling. First kind. All right, so Stirling first kind. Stirling first kind. So in the Stirling, oh, wait, why rest in peace? Did I mess up? Okay. All right. What is Stirling first kind? Pretty much the same thing. And distinguishable objects. Okay, indistinguishable. What do you call it? Circles. Kidding me? Such that no circle empty. All right, that's it. So the question then is, how many different ways can you place objects into circles? Okay, let's do it. Let's do for the case 4 again. Okay, so let's start with 4, choose 1. How many ways can you put 4 distinguishable objects into a single circle? One way? No. Yes, it's not, we're not putting into just a simple box no longer. We are putting it into circles. Yes, 4 minus 1 factorial, which is 6 ways. That's it. So this one is a 6. Okay, let's do 4 objects into 2 circles. How many ways? Do you see how I use these square brackets now? How many ways can I put these 4 objects into 2 circles? First, we need to partition 4. How many cases do I have? 2 cases. Either one circle would have a 3, the other circle will have 1 object, or the second case we will have 2 and 2. Let's do 3 and 1 first. How many ways can I have this? 6 ways. 6 ways to, wait, no. 4 ways to decide which one will be the lonely guy here. Suppose that A will be here, the lonely guy, A on that circle. The remaining 3 objects will be put here, B and C and D in this case. How many ways can I order these 3 objects? So 4 ways to choose which one will be lonely. And then these 3 objects can be ordered in 3 minus 1 factorial ways, which is just a 2. So that's an 8. Or we can do 2 and 2. Oh, sorry, this is 8 is the first case. Plus, or we can split them as 2 and 2. How many ways can I split 4 distinguishable objects into 2 portions of 2 and 2? I think I can split them in 3 ways, right? Yes. So I can split them in 3 ways. For those of you who are wondering how can we only split, so we can do AB in one of them, CD in another one, or we can have AC in another one, BD in another one, or we can have AD in one circle and BC in another circle, or we can have BC in one circle, AD in another circle. Wait a second. That's not gonna work. Why? Because we already counted this one, right? They are indistinguishable, the circles. So there's only 3 ways to do it. Once we do it, suppose that A and B goes into one of them and C and D goes into the other one, you are right. So there's only 1 way because 2 minus 1 factorial is just 1. Yes. So there's 3 ways as a 3 times 1 square. Long story short, that's just 8 plus 3. That's 11. That's it. Well, we can in a similar way do 4 choose 3. 4 choose 3. So if you have 3 circles, how many ways can you do that? Wow, 80 answers in one question. Oh, shoot. Okay, so that's a lot. All right, and then the answers are keep coming. Yes, so if you have 3 circles, you need to choose which 2 will go into one, and then the other ones will just have the remaining 2 in any order, doesn't matter. So it is just 4 choose 2, which is just 6. That makes sense. And lastly, 4 choose 4. If you have 4 objects, 4 circles, how many ways can you do that? That's right, 1 way. Whew. Okay, so therefore, let's now build a Stirling first kind triangle. Stirling, oh wait, before we build it, we need the recursion. Stirling first kind recursion. The recursion will be very similar to the Pascal identity and the first Stirling second kind identity. Let's quickly have the recursion. So let me tell you what it is and you explain to me where it comes from. M plus 1 objects into K circles or cycles. Sometimes these are called as Stirling cycle numbers. So M plus 1 into K cycles would be n times n into k cycles, and then plus n objects into k minus 1 cycles. What's the logic here? What's the case work? Okay. Yes, the case work is guess and check. No. Yes, again Joe, right? No, not again Joe. Woody. Yes, Woody. Either Woody is lonely in his own cycle, so which means what? There's n toys left, and k minus 1. N toys left and k minus 1 cycles available for them. So that's it. So this is the case where Woody lonely. So first put Woody into one of the cycles without loss of generality. There's one way to do it, and the remaining n toys can be placed in k minus 1 ways into the remaining cycles. Or Woody is in a cycle with some other toys, which means first let's place all the other toys into k cycles, and finally Woody have n choices. Why n choices, not k? I thought there was k cycles. 15,000 messages in the second part. In the first video, I think we had again about 15,000 messages. That's why my computer crashed. I will change my computer for the next week. Do you guys agree that because exactly, so all you do is you place Woody to the right side of one of those n toys which are already placed in those k cycles, and that's it. So that's a pretty good argument as well. So this is a recursive form from which you can construct a triangle. Let me quickly construct the triangle for you, and then you guys answer. For instance, 1, 1, 1, 2, 3, 1. We already did this one. 6, 11. What is 6, 1? Let's do the next row based on the fourth row. So if you have 5 objects, how many ways can you place them into a single cycle? 5 objects, single cycle. I need the very first number here because recursion doesn't tell me about that. Unless I define the zeros, choose 0. If you have 5 toys, a single cycle, how many ways can you put those 5 toys into that single cycle? Hey, no one is listening to me? I have a question here, a legitimate question. 5 toys, a single cycle. How many ways can I do that? What happened? Oh, thank you. 24. Yes, that would be 24. 5 minus 1 factorial. Yes, that would be exactly. And then, okay, next number. So this number, all I will do is just to use this recursion, and it should be very dandy and cool. And because we are in the fifth row, all I will do is 5 times and choose k. So 5 times this number, which is 55, and then I'll add this number to it. 55 plus 6 is, oh, sorry, the previous row. So this is the 5th row, so I need to multiply by 4, sorry. 4 times 11 plus 6. Do you guys see that? That is 50. Then for this one, it would be 4 times 6, which is 24 plus 11. 24 plus 11 is 35. And finally, 4 times 1, which is 4 plus 6, that's a 10. And finally, the last row is always a 1. Holy, is this also triangular numbers? Maybe it is. So again, oh, no. Yeah, maybe it is. I don't know. I didn't check. Okay, unless you guys want to check it. No, we don't. Now, finally, the challenging problem of today. Yay, Dr. Nal, we can't wait. Yes. Okay. The challenging question, it's a 2-step question so that no one is lost. My first question is this. Suppose that you have, and this is the second book that I benefited for today's lecture. This is Art and Craft of Problem Solving. So the first book was the Book of Numbers. It had 2 authors. I only know the first author, Conway. There's a second guy. I apologize to that second guy. I forgot his name. The second book that I benefited from is The Art and Craft of Problem Solving. It's like the art of problem solving. It's except it's art and craft. So this one is by Zeitz. That's also a pretty good book as well. All right, so there's an exercise at the end of the Zeitz book. It's on chapter 6, and we're going to solve that exercise, basically. That's it. It's a long exercise. Let's quickly do it. The question is the following. You have n kids. They want to eat ice cream cones. Okay, so this is problem, let's call it problem 10. N kids, and they want to eat ice cream. In total, there are k different flavors, k different ice cream flavors of ice cream. Then the question is, assuming that no flavors get mixed. So when you order ice cream, you have to only order one flavor. Show that the number of ways, what is the number of ways you can give out the cones using all flavors? What? There's an unlimited supply of each flavor, don't worry about that. What is the number of ways to give each kid a cone, to give out the cones, the ice cream cones, such that you need to use all the flavors, using all flavors, question mark. So let's see if anyone will be able to, oh gosh, that's my last page, last part. Oh gosh, 5 pages of handouts. Oh, wait. So you want to make sure that each kid gets an ice cream, and they can only pick one flavor. Oh, okay, already there are some solutions, all correct answers on the, and you want to make sure all the flavors has been used. Yes. Okay, do you guys agree that the answer would be, well, the second kind, the Stirling numbers of the second kind multiplied with k factorial? Well, the reason is the following. The boxes now are distinguishable. So Stirling gives you how many ways to give n objects, n objects to place them into k boxes, or n kids choosing the k cones. However, here the boxes are indistinguishable, but we are saying that the flavors are distinguishable. They are distinguishable. So that's why we need to multiply it with k factorial. Aha. Okay, so now my second question. The second question is the following. So if I ask you, all right, so if I were asking you a general question, if I ask you, if there are n kids and k flavors, how many ways can the kids choose the flavors? N kids, k flavors. How many ways can the kids, without any restriction, choose the flavors? N kids, k flavors. Okay, in the meantime, I will search for some space. I'm out of space here. Okay, let me put it over here in this space. All right. Yes, do you guys agree? Okay, so let's do it over here. All right, so let me make it slightly larger here. Oh gosh, come on. Okay, there you go. All right. It would be k to the n. Now, just like we did earlier, I'm gonna split that k to the n into different buckets. Okay, so that's the last part. We will be just 1 minute over time, I hope. So I claim that, so first question, in how many of them, how many ways can we have only one flavor given out to the kids? How many ways can we give out to the kids just one flavor? No, no, not one way. There are k distinguishable flavors. Yes, all the kids will get just the same flavor in k different ways. That's correct. So, okay, so let me split this into different subsets. A1, let me call it, where all the kids just get the same flavor is k different ways. So how about all the kids, they just get r different flavors? How many ways can this happen? Where the flavors are distinguishable? I think by now you guys know what I'm doing. So I will also, because we are choosing R flavors, it's exactly what we did, right? So it is n choose R times what? because the flavors are distinguishable, r factorial times, wait, times and choose r. Wait, why are we choose? Yeah, times and choose r. Why is that? We need to choose which flavors as well. Do you guys see? Which of the R flavors? We can choose the R flavors in this many ways. Once we choose the flavors, this many ways to YK. Oh, we have K. Oh my God. Oh yeah. K. I'm sorry. Yeah, there are in total K flavors. Yeah. My bad. Yeah, there you go. And that's it. So therefore, you can expand this K to the end. We can plug in all of this. And finally, you would come up with the very strange formula, an amazing formula. Okay, so it comes out with the following amazing formula. And choose one. So this is actually the proof of this formula. Let me write it out, and then I will tell you what this means. And choose 2 times x to the 2, and then with this minus sign underneath, and so on. So plus plus finally n choose n. So this is basically just a combinatorial identity where the meaning of this notation x r bar is just equal to x times x minus 1. So this directly comes by multiplying these two. If you were to multiply these two, you would exactly get these terms basically. X minus r plus 1. That's it. Okay. Well, let me just quickly check something. Yeah, wow, we have quite a few people here. Let me stop the recording.